We physicists have waited 100 years since 1916 for this photograph.
On April 10th, 2019, the world's attention focused on a single image, a ring of fiery orange-red light encircling a region of absolute darkness. This was the first ever real photograph of a black hole. Named M87, it lies at the heart of the Messier 87 galaxy, 55 million light-years from Earth. M87 is one of the most colossal objects ever discovered, weighing 6.5 billion times the mass of our Sun. If we placed it where our Sun is, our entire solar system, out to the orbit of Neptune, would fit comfortably within its shadow. This isn't a star or a planet. It's a massive dent in space-time itself, a place where light, matter, and even time cannot escape. It sounds terrifying, but the fascinating thing is, we don't actually see the black hole. We see the matter being devoured by it, as gas and dust are pulled into a swirling vortex. They spin so fast they heat up to billions of degrees, glowing brilliantly and forming a ring of fire around the dark center. That light is what casts the black hole's silhouette, just as you see the shadow of an object, not because the shadow shines, but because it blocks the light around it. That very shadow is what humanity has been trying to find for over a century. Back in 1915, Albert Einstein's theory of general relativity predicted the existence of these gravitational monsters. But even he didn't believe we could ever see one. They were too far, too small, and completely invisible. Yet, more than 100 years later, thousands of scientists from around the world achieved the impossible. They captured the shadow of a real black hole. The answer lies in one of the most audacious projects in human history, the Event Horizon Telescope, or EHT. It isn't a single telescope, but a global network of radio observatories scattered across the Earth. From the Atacama Desert in Chile to the peak of Mauna Kea in Hawaii, and even a frigid research station at the South Pole, all of them synchronized like a giant planetary eye, all staring at the same target, the heart of the M87 galaxy, where the black hole M87 was hiding. Instead of capturing visible light like a normal telescope, the EHT listens to the universe in radio waves, a form of light with a much longer wavelength. These waves can pierce through the dense clouds of gas and dust that shroud the black hole, something ordinary light cannot. This allowed the EHT to detect the faint signals coming from the matter swirling at the edge of the event horizon, the boundary beyond which nothing, not even light, can escape. To link telescopes across the planet into a single virtual instrument, scientists used a technique called Very Long Baseline Interferometry, or VLBI. Simply put, they synchronized each facility with atomic clocks accurate to a billionth of a second, then combined their data to create a virtual lens the size of the entire Earth. This precision gave the EHT an unprecedented resolving power if you placed a grapefruit on the moon. The EHT could see it. This is a feat that even the Hubble Space Telescope, the icon of modern astronomy, couldn't touch. Hubble sees the universe in visible light, but the black hole is pitch black and veiled by thick cosmic dust. It's like trying to see through dense fog with your naked eyes. The harder you look, the blurrier it gets. The EHT, however, uses radio waves like a radar, probing what lies deep inside that dusty veil. But photographing a black hole wasn't just difficult because it's dark. It was also a challenge because of the colossal amount of data the EHT collected. Each night of observation, the stations around the world recorded petabytes of data, equivalent to thousands of years of HD video. This flood of information was too massive to be sent over the internet. Instead, scientists had to physically fly hard drives to data processing centers in the United States and Germany. After 2 years of synthesis, calibration, and analysis, millions of individual radio signals were pieced together to form one single image, the ring of fiery orange light surrounding the perfect darkness of M87 Taos. When that image was unveiled, the world fell silent, not just because of its beauty, but because of its profound meaning. Humanity had finally seen what was once believed to be unseeable. That ring of light wasn't just glowing hot gas. It was a testament to the theory of relativity, proof that Einstein was right, and a demonstration that humans, with sheer persistence and intellect, could touch the very edge of space-time. From this point on, the story was no longer about seeing a black hole. It was about understanding what was happening inside that ring of fire where matter is torn apart. Energy explodes, and the universe seems to be writing its own rules. And that is where our next chapter begins, the mystery within the ring of fire, just outside the black hole's boundary. Where light itself begins to bend, lies a region of pure chaos. Here, gas, dust, and plasma particles hurtle at nearly the speed of light, colliding, spiraling, and igniting at temperatures of billions of degrees. The immense gravity of M87 stretches matter into giant, spaghetti-like strands, compressing and heating them until they glow with ferocious intensity. This swirling maelstrom of material forms the accretion disk, the brilliant ring captured by the EHT. It would seem that anything drawn into this vortex would be lost forever. But strangely, not everything is consumed. A portion of this colossal energy is blasted back out, forming powerful jets of plasma that shoot deep into space at nearly the speed of light. Each jet stretches for tens of thousands of light years, so powerful they extend beyond the edge of the M87 galaxy itself. If you look through a telescope, you can see these streams of light like cosmic blowtorches, cutting through the cold, dark backdrop of space. Scientists call this mechanism the Blandford-Znajek effect. As the black hole spins, it drags space-time along with it, twisting the magnetic field lines around it. This twisting action works like a gigantic generator, extracting rotational energy from the black hole and launching it outward as massive plasma jets. In other words, the black hole once thought to be an energy abyss can actually create energy, turning the very fabric of space-time around it into a source of intense power. The latest images from the EHT, collected between 2017 and 2021, reveal that M87's magnetic field is anything but stable. The field lines are constantly shifting, reversing their polarity like a swirling tornado. This phenomenon, known as a magnetic flip, happens millions of times faster than it does on Earth. It shows that the accretion disk around the black hole is a vibrant, dynamic plasma vortex, constantly flaring up and dying down to its own rhythm like a beating heart at the center of the cosmos. At the same time, the James Webb Space Telescope, JWST, has observed M87's plasma jet in the infrared spectrum, revealing clear, layered structures within the matter, stream knots of light where energy becomes intensely concentrated before being fired into space. Each image from Webb is like a single frame in a film, capturing the moment the black hole moves, breathes, and expels energy. It turns out, M87 is not the dead, empty void we once imagined. It is a colossal energy engine where gravity, magnetism, and matter are locked in a relentless battle. Hidden behind the shadow is a dynamic ring of fire, and the heart of an entire galaxy beats in time with it. After their success with M87, the EHT team turned their sights toward the center of our own Milky Way galaxy. In 2022, they released the first image of Sagittarius A-E's, although the picture was blurrier and changed more rapidly due to the chaotic motion of the matter around it. It was a second historic milestone for the first time. Humanity had seen its own galaxy's black hole. With these two images, scientists could now compare how two different black holes eat and breathe. On one side, a dense, fiercely burning flow of matter. On the other, a quieter region of space, punctuated only by occasional, short-lived flares. These differences are helping them understand how energy is generated, consumed, or ejected in supermassive black holes. But the EHT isn't alone in this quest. Other telescopes like Hubble and James Webb have played crucial roles. Hubble observes the visible light from the jets erupting from M87. JWST peers deeper in infrared to reveal their structure, while the EHT listens for radio waves from the dark region right at the event horizon. By combining all of this data, scientists can construct a three-dimensional picture of a black hole, much like assembling hundreds of X-ray and MRI scans to reconstruct the human body. This collaborative effort has made one thing clear: no single type of light can tell the whole story. Each wavelength is another piece of the puzzle, and only by putting them all together can the picture of M87X and Sagittarius A truly become complete. These two giants in the shadows, though separated by tens of millions of light-years, are helping humanity understand the very structure of our universe and the limits of our own knowledge. The release of the M87 FAD image wasn't the end. It was just the first chapter in the journey to discover what lies beyond the darkness. Humanity has seen the shadow of a black hole, but what scientists want next is to see it move, to watch matter fall in, to see energy jets erupt, and to witness space-time itself being bent, second by second. To do this, they are developing the next-generation Event Horizon Telescope, or EHT. This project will expand the current EHT network by adding many new telescopes around the world, and even one in Earth's orbit, if the first EHT gave us a static photograph. The EHT will deliver the first movie of a black hole, capturing the real-time motion of matter as it spirals past the event horizon. Imagine it a film showing a stream of incandescent gas falling into a black hole, its light bent into a perfect circle before vanishing into the shadow. Each frame will help physicists understand how energy is released and why black holes can launch colossal plasma jets that span tens of thousands of light-years. Perhaps, within those images, they will discover things that current theories have never even predicted. These new efforts go beyond just testing Einstein's theory of relativity. Some scientists hope that by observing the precise way light bends around a black hole, we might detect signs of dark matter, the substance that makes up most of the universe's mass, but remains completely invisible. It's possible that right at the edge of the event horizon, where all known rules of physics break down, we will find our first clue to this mysterious component of our cosmos. The EHT is planned to begin operations in the early 2030s. Scientists predict it will produce images 10 times sharper than the one from 2019, sharp enough to see individual plasma swirls and every pulse of the magnetic field around the black hole. This will be humanity's next great step after seeing the shadow. We will finally watch the shadow move. But beyond all the data, numbers, and theories, what resonates most deeply is the human story behind it all. In a vast and cold universe, a tiny species like ours dared to point its instruments at the sky, to stare directly into the abyss, and to bring back a picture of darkness itself. This isn't just a scientific achievement. It's a symbol of our endless drive to explore, fueled by intellect, curiosity, and the belief that no boundary is forever. The universe still holds countless mysteries, smaller, faster black holes, or perhaps even ones that could reverse time. But M87 is a powerful reminder every time we dare to look at the impossible. We see ourselves reflected back, curious, bold, and hungry for understanding. If you want to continue this journey, be sure to like, subscribe, and join me as we explore the cosmos, where everything we once thought impossible might just be waiting to be discovered.